reduces an amount of power which is drawn from the circuit, and which can be tested by increasing the input impedance. So here Z equals to here V equals to YR, or R equals to V by I. Similarly, here also in place of R we are substituting the Z here. Impedance Z equals to V by I. So that input impedance which may be here increases by using an amplifier with unity gain here. Gain is nothing but a output voltage by input voltage, which is gain here. So a source follower which can be derived the emitter follower, and the combination which is capable of achieving the 1,000-fold increase input impedance. Okay, and it is also going to be maintained the voltage gain which is nearly 1 here, and the input impedance 10 mega ohms, and which would be require the 0.025 microwatts wattage of power for a 0.5 voltage deflection, and as compared to the here 0.25 micro wattage for passive meter, and is also increases the sensitivity of the 100 times in it is going to be achieved through this arrangement here. Okay, so because of this emitter follower, so which must have the biasing current power pressure, and the emitter voltage which doesn't go for the 0 volts and 0 input voltage. Yes. So thus the other terminal of the your meter must be returned to ground, and but a voltage that can be set to equal to the quotient point of the output. Output is VE here. Okay. So in many practical meters, this made adjustable from the point. So because of the setting of the zero control effects and the total resistance in series the meter, and it is going to be calibrated control is also supplied here, and this is not necessary for amplified meter by using a differential amplifier, because of there is no interaction between the zero adjustment and the calibration. So this case you may be on board here. Right. So that is the case. So this is the complete circuit diagram for the. Next is the differential amplifier, which is how it is going to be balanced. A bridge type EVM, electronic voltmeter. Electronic voltmeter. So one of the most versatile general purpose measuring instrument, which is capable of measuring DC direct current as well as the alternating current and resistance in the solid state electronic multimeter, or else VOM. Okay. So the which can be here, what are the following elements this is consisting of means, which is a balanced bridge DC amplifier and indicating a meter. And the input attenuator or the range switch to limit the magnitude of the input voltage to the desired value. And rectifier section here, which may convert an AC input voltage to the proportional to the DC. Normally, we know about that here. What is a rectifier means here? A rectifier is nothing but a PN junction diode, which is going to be converting the pulsating AC into DC. So the same thing is going to be happening in this case also. So internal battery and additional circuitry to provide the capability of resistance maintenance. And the function switch, another one is the function switch. to select the various measurement functions of the instrument, such as voltage, current, or resistance, or DC or AC. So, in addition to that, which has a built-in power supply for AC line operation, and in most cases, one or more batteries for the operation as a portable test instruments. So, this is the balanced bridge amplifier. Okay. This is the central one. Okay, na? With input attenuator and indicating wheel. How it is going to be attenuating the signal or the voltage, and how it is going to be indicating. So, which is a schematic diagram for the balanced bridge amplifier and DCM. So, using the FET, field effective transistor. So, a bridge amplifier with ordinary bipolar transistor, BJT bipolar junction transistor. So here this circuit which consists of two balanced FETs, two FECs, which should be reasonably well matched for current gain and to ensure the thermal stability of the circuit. And here two FETs from the upper arms. Here this one. You can see here two FETs here. Field effective transistor. This is the upper portion. This is the bottom portion. Okay. Of a bridge circuit. So source resistors are R1 and R. Here are there with 0 with the adjustment resistor is R3 here. This one central. R1 and R2. This is the R3. This is at lower bridge. Whereas the meter movement which is connected here between the source terminal of FET and here source terminal of FETs and representing two opposite corners of. Okay. So without an input signal, the gate terminal the both FETs which are grounded potential and the transistor operate under the identical quotient conditions. You please remember this. So in this case, the bridge is going to be balanced and meter indicates the 0. Okay, that is the case. For however, a small differences in operating characteristics of transistors and a slight tolerance difference in the various resistors, which may cause a certain amount of unbalance in the drain current. And meter shows a small deflection from 0. To return the meter to a 0, the circuit is balanced by 0 and adjusting control R3 for a true null indication. Null means 0, nothing is there. Okay. So whenever a positive voltage is applied to the gate of the input transistor Q1, the drain current increases and the voltage at the source terminal to rise. So the resulting unbalancing between the transistors Q1 and Q2 sources, which may be indicated the meter to movement, and the entire scale is calibrated to agree with the magnitude of the applied input voltage. So what is the maximum voltage which can be applied to the gate of the Q1 and which is determined the operating range FETs and is usually in the order of few volts. So the range of the input voltages which can be easily extended by input attenuator or range switch. So the unknown DC input voltage which is applied to through a large resistor in the probe body to a resistive voltage. So the potential divider network in the range selector, which is divided, designed with a very high total resistance of 10 mega ohms. Further, a series resistance of 1 mega ohms, which is also included in the gate input terminal, and which is minimize the loading on the input signal source. So here, which may be modified, the circuit, we can measure the AC voltages, currents, and resistance by using this. So what is the summary of this chapter means? Here the designing of the passive the arsenal type of measuring instruments, and like to measuring the electronic measuring instruments which are studied in the unit and which may be introduced the student to the field of the measuring. And the multiplier resistors which are usually mounted inside the case of the higher voltages. The multiplier may be mounted separately outside the case of a pair of binding to avoid excessive heating inside the case. And at a higher frequencies, the inertia of the coil, which is so great that the pointer cannot follow the rapid reversal of the driving force, and which is around the zero mark. So the DC moment, which is indicating the value of the rectified is. And here the control, which is not necessary for the amplified meter. By using a differential amplifier, because there is no interaction between the zero adjustment and the calibration of the meter. So what is the unknown input voltage which is applied through a large resistor in the probe body to a resistive voltage? What are the model questions in this? So give the design consideration to for a converting D'Arsonval type PMMC meter into ammeter, and also converting D'Arsonval PMMC voltmeter. Okay. D'Arsonval type PMMC meter. Voltmeter, one is the question, another one is the ammeter. So permanent magnet or a coil. Next is the digital measuring instruments. So digital voltmeter classification, linear ramp type DVM, staircase range type of DVM, and a dual slope type DVM, successive approximate type DVM, simple frequency. Let you give me the introduction about the DVM, digital voltmeters. Okay. So here, so all the analog measuring instruments which are being replaced by digital instruments, and hence on the emphasis has also been given to the design principles of digital instruments. So digital voltmeters nowadays, in most of the cases we are using these. These may give the accurate value compared to the analog systems. Okay. So here, how many types of digital voltmeters are there? If you go for it, you can be classified into RAM type, integrating, continuous balancing, successive approximation. So these are the types which are included in the digital voltmeter. So whereas the oscillator which may generate the clock pulses and which are allowed to pass through the gate uh, to a number of decade counting units. So a sample rate multivibrator which may be determining the rate at which the measurement cycles are initiated. And one method of reducing the dependence of the accuracy of the conversion and the resistor, capacitor, and operational amplifier is use a technique is called dual slope converter. Then digital your voltmeter and classifications. So the DVM, digital voltmeter, DVM, which displays the measurements of the DC or AC voltages instead of a pointer deflection only. Continuous analog devices. So here the to reduce here in this analog devices which may have a pointer deflection, and here to reduce the human reading errors, interpolation errors, and which you are going to be eliminating the parallax errors, increasing reading speed, and often provides output for the uh, further processing or recording. So these are the main advantages of the DVMs here. And DVM is a versatile and accurate instrument with development integrated circuit models. And the size, power requirements, and the cost of the DVM, which have been drastically reduced. So the DVM outstanding qualities, and which can be best be illustrated by quoting this some typical operations and performance characteristics. So what is the input range here? Plus or minus 1 volts to here 10 lakhs volts up to this. Okay. Automatic range section and polarities overloaded. So what is the absolute accuracy? Plus or minus 0.005%. Stability is also very high. Here 0.002% of the reading for 24 hours period. Resolution is also very high, 1 for 10 power 6. Input characteristics, that is input resistance is approximately 10 mega ohms. And what is the input capacitance? 40 picofarad. Okay. So the calibration internal calibration stabilizer reference source allows calibration independent of the measuring circuit. So here the output signals, which may be indicating that here output to printer binary coded decimal BCD. Okay. So output also available for digital processing or record. So here 1 minute. So here the output signals which may be printed command output to the printer here. So digital DVMs which may be classified according to the this ramp type DVM, linear ramp and staircase ramp. Integrating DVM, single slope and a dual slope, and continuous balance DVM is also there. Successive approximation DVM digital mean. Okay. So the linear type ramp type DVM we may discuss here. The thing is that The principle of operation of the ramp type here, which is DVM based on the measurement of the time, and here it takes the linear ramp voltage arises to 0 volts from the level of input voltage or decreasing the level from the voltage to 0 volts. So what is the time interval which is measured with the electronic time interval current, and which is going to be counting a display the number of displays, and the conversion voltage time interval, this figure which is going to be shown. The voltage is a positive going or negative going ramp. Oh. So here the conversion of the from a voltage to time interval. At the start of the measurement cycle, ramp voltage can be positive going or negative going. And here the scene. So this is the clock pulses to the counter here. Voltage to time conversion using gated clock pulses. So this is the gating time interval. This is minus to plus volts here. This is the ramp voltage here. This is the ramp here. Okay. The start of measurement where it is coinciding, and this is the pulse here. Okay. So the ramp voltage continues to decrease with the time until final reaches the 0 volts. And the second comparator generates an output pulse, closes the gate. Then oscillator generate the clock pulses, and which are allowed to pass through the gate to a number of decade counting units. DCA means decade count. This one. So the number of pulses passed through gate are displayed by distance. So the simple rate, sample rate multiplied rate, which is measurements is cycle simulation. Here sample rate measurement. Okay. This is the ramp generator. And the voltage which is feeding through the ranging and attenuator. So this is the input comparator, op amp. This is the ground comparator. Two op amps we are using. This is an oscillator, and here is a gate here, a starting pulse and a stopping pulse, and there is a counter, and which has been recorded by the which is signal which you are taking from the counter. Okay. So which may provide the sample rate circuit, which may provides an initiating pulses for ramp generator, and it may starts to its next ramp voltage. Yeah. At the same time, the reset pulse is generated, which returns all the display counting unit to their zero state. Next is the staircase range type of DVM, which is the modified form of the from the ramp type DVM, but is somewhat simpler in overall design. Hence, it is moderately priced. And here the DVM makes voltage measurement by comparing input voltage with an internally generated staircase ramp voltage. So which may contains the 10 mega ohms input attenuator, and which is providing 5 input ranges from 100 millivolts to 100 kilovolt full scale, and DC amplifier which is fixed gain of 100, which may deliver the 10 volts to the comparator at any of the full scale voltage which is setting up the input potential divider. So here the comparator which may sense the coincide between the amplified input voltage and which is generated the measurement of the frequency. So whenever the measurement of cycle is first is going to be initiated, a clock of 4.5 kilohertz relaxation oscillator, which provides the pulses to the three digital counts units in cascade, the overrange circuit, which causes a front panel indicator to light up that the input capacity of the instrument has been exceeded, and in advanced version of the DVMs. So the outputs of the DA converters are connected in parallel to the provide an output current proportional to the present output of the DCUs. Staircase amplifier convert the DA current into the staircase voltage, which is applied to the comparator. So when comparator senses and coincide the input voltage, the staircase voltage it provides trigger pulse to the stop the oscillator, so that the oscillator may not work. So the present content of the counter then proportional to the magnitude of the input. So the sample rate which is controlled by the sample relaxation oscillator. So this oscillator triggers and reaches the transfer amplifier at a rate of 2 samples per second. 2 samples per second. So which may the transfer the amplifier provides pulses, and that may be transfer the information to the stored decade counter and to the front panel display. So the trailing edge of this pulse triggering reset amplifier, and it may sets the decade counter to the 0, and it which may be initiating the measurement cycles by this. Okay. So the display circuit which may be storing the each recording until a new reading is going to become. So and by eliminating and blinking the during the completion. What is the disadvantages which are associated with this ramp type of A to D converter, which may be requires a precision ramp which is achieve accuracy, and this requires a precision stable capacitor and resistor in the integrator. In addition to this, operation amplifier used in the integrator, which are crucial. So the circuit is reversed here. Diagram is reversed. Okay. So this is the input signal, and this is an input in the attenuator, and this is the DC amplifier, and which may fed to the comparator here. And again the comparator which may have a flip-flop, and here 4.5 kilohertz oscillator is there, and the single units decade counter and tens decade, hundreds decade over the above range, and which may be fed to the DTA converter. Here over range 100, tens, ones, and which may be sent to the staircase app, and which is giving to the comparator. And here is a digital display there, and this is the reset button. Okay. So transfer amplifier and the reset amplifier is there. So transfer line which is connected to the digital display, and the reset line is there. Okay, if you want to reset it, is it will, again it will come to the comparator quickly. Okay, na? Right. In examination point of view, you can go for that. Next is the dual slope DV type DVM. So one of the method which is reducing the dependence of the occurrence of the conversion on the resistor capacitor RC combination. Operational amplifier. Input we are considering R, and we are fed back through the capacitor output signal. So that is RC means integrated. Differentiator means CR, capacitor and resistor. Okay. So which is used a technique called a dual slope. In this, an integrator is used to integrate and accurate reference voltage to a fixed period of time. Okay. So this is the 0, and slope is the minus VI by RC, and this is the plus VR by RC. 0 to time is fixed time T1, and this is the Tx. Okay. So here an integrator which is used to integrate an accurate reference voltage for a fixed period of time. The same integrator which is used to integrate with the reverse slope, the input voltage, and the time required to return the starting voltage is method. And it is does not matter that which of these two integrators occurs first, and for easy understanding the unknown voltage first, and then the reference will be considered voltage is integrated next. So this is the first, this is the second. Okay. So what is the output integrator here? Vx tau by RC. What is Vx? Steady input voltage. V out is output voltage. RC is time constant. Why? Because of tau equals to RC. Okay. So in above equation, the integrator capacitor started with no charge, and the output integrator started 0 volts. Again, if no charge, the output integrator started 0 volts. So here, if the integrator which is allowing to continue for a fixed period of time, that is a Ti or a T1, the output voltage will be Vx by RC into T. So this has gone to opposite polarity to the input, and the positive input voltage which may produce the negative integrator out. So what is the reference voltage? V reference, which were substituted for the input voltage Vx. The integrator would begin to ramp toward the 0. V reference by RC, and assuming the reference voltage was up. Opposite polarity, and it is unknown to the input voltage. So the integrator for this situation, and it does not start at 0, but the output voltage V1 and output voltage can be represented. Output voltage V1 plus V reference by RC into T, or else V1 plus V reference by RC into Tx. So finally Tx by T1. Okay. So this may shows the complete dual slope A to D converter. This may shows complete one minute. So this is the electronic switch here, and this is the reference voltage, and this RC combination. This is R and C. This is op amp. So this is an integrator, and which may fed to the AND gate, and which is going to be counting the counter, and which may be displayed here. And if it is resetted, and this is the clock generator to the control logic unit, and which may fed to the electronic switch. So in this above figure, you can have a complete dual slope A to D converter. Okay, this may shows the A to D converter electronic indicator here. Next is the successive approximation type, DVM. So a very effective and relative uh, a cheaper method of analog to digital conversion, which is the method of successive approximation. So this is an electronic implementation of the technique, which may call the binary regression. Okay, and, which is going to be determine the value of the number, and it is allowed to make estimates. And each estimate would be evaluated and it will be equal to or less than or greater than the number which is to be determined. And the maximum and minimum value of the possible number is also known. That we are going to be consider. This is a small example here. Which going to be number to be determined between 0 and 511. The average, what is the average here between? Approximately 256. Okay, approximately. So further assume the number to be determined 499, which is close to this one, and which is greater than the estimated value here, 256 and 511. Again, some mid makes with most sense for the guess, which is 384, and the number to be determined which is greater than the estimated, and the next range which is the estimates here. What is that? So 384 to 511. And for the midpoint 448 to 5, and again the larger than this the next range which is possible from the 448 to 511. What is the midpoint? Approximately 480, and the number is larger than this, which is leaving the next range of possibility from the 480 to 511, and the midpoint which may guess the 496. Again, the number is larger and next range from the 496 to 511, and midpoint guess is 4504. Like that here, the time unknown number which is smaller, and the range from the next information is 496 to 504 with a midpoint of 500. And where the number is smaller than the estimated leaving range possible 496 to 500. The result of the midpoint which may guess the 498, and if the unknown number is greater, the last possible range is from 498 with a midpoint of 490. So this is the ninth estimated, and this is known as 500, greater than that of 490. So here this is the input here, which is greater than or less than or equal what will be here top end, and a DTA converter, digital to analog converter. This is the successive approximation register, SCR. Okay, so where we are leaving this, and this is the decision logic, and this is the clock, and if you want to clear the SCR, we are using this. So here sequence of the event perform electronically. Very good, so which is estimating the procedure, and that outlined previously the estimated made age of the SAR clock. If n bit conversion after the n clocks, what is the actual value of the input in known? The LSB value, least significant bit, which is the state of the comparator. In some systems, an additional clock is also used to short the last bit in the SAR, and then n+1 clocks which are required. Next is the temporal frequency counter. So here standards of time and frequency, which are unique in that they may be transmitted by radio from one location to the another without the actual movement of the standard. Therefore, it is possible to have traceability to the primary standard without difficulty. The primary standard, which is related to the structure of the matter, and primarily standards can be easily duplicated throughout the world to allow high accuracy measurements. Because of these relatives, frequency and the time can be measured to great accuracies. Electronic system have developed around the camera. So one example which is going to be given out here. You have to find out that which one is this is a logical block diagram of the digital frequency. So here this is input signal conditioning uh, accuracy, and this is AND gate here, and the counter and the display memory. The JK flip flop, and this is the reset button, and this is the latch Q and Q bar. Okay. So crystal oscillator is 1 megahertz signal conditioning circuitry. These are the conditions. So how we are going to calculate it means whenever a Q output is high, the gate is open. This result counter counts for 1 second. After end of the 1 second period, Q output goes low position. So that which is disabling the gate. When the Q output, which is complementary to Q, is utilized to reset the counter, the Q bar output goes high. When Q goes low, this triggers the monostable multivibrator, whose output is used to latch the next information to the counter. And it is also utilized to reset the counter when the counter is ready to begin the next count cycle. That is the case. This is the summary here. All types of digital voltmeters, digital frequency meter, thoroughly discussed. And at the instant that ramp voltage equal unknown voltage, which is coinciding circuit or comparator generates a pulse which open gate. The number of pulses passed through this gate are displayed by digital display. And the sample rate is controlled by sample relations. So dual slope method, which is also slow, but it's a quite adequate for a digital voltmeter, which is used in laboratory. Give circuit diagrams, design linear ramp type digital. So what is the advantage of staircase? Give the principles and working of dual slope deviant. What is the disadvantage associated with the deviant? Okay. So these are about. Next is the block 3 digital electronics. There only we can able to discuss with the number system logic is binary to decimal conversion, decimal to binary, binary addition and subtraction, direct subtraction, BCD, binary coded decimal, octa number system, conversion of octal to decimal, decimal to hexadecimal, Boolean algebra, De Morgan theorem logic. All comes under this. So by coming class, and definitely it will take the 2 classes to complete this one. Through PPT only I will discuss all this. Okay. So by coming class we will discuss this.